about this new concept as well. I should wait here, though. Are there any questions about volume before we go on to this new concept that I was describing? People okay with calculating volumes? There's really only two. We're going to do cubes and spheres, and that's it. We're not going to do anything else. Yeah?
This is like a little bit out of the blue, but is the Earth really flat?
We can definitely talk about that. It actually takes a little bit longer. The answer is no, the Earth is a ball. And the reason we know it is because there are certain measurements that we can do.
I saw like a bunch of memes.
Of course you have. But let's actually answer this. I'd like to go through and give an answer to that. Maybe I will film that one as like lecture number 5. But I want to finish this discussion first. We'll involve the Earth in this discussion. We're going to assume for right now that the Earth is a ball. I can show that it's a ball if I do certain measurements, but I'm going to have to leave that aside for right now. And we'll actually think about some of the things we can learn about the Earth using this concept. And you're absolutely right to sort of worry about this because, yeah, you've seen all sorts of interesting things on the internet. And how do we deal with that? We'll get back to that. Okay, so we have this idea of volume. Any final questions on volume?
So volume is used to measure like the third dimension.
It's the way to measure how much space something takes up that's a three-dimensional object. If I have a two-dimensional object, a piece of paper actually is three-dimensional, but we often ignore one of the dimensions. If I wanted to figure out how much space a piece of paper took up, I would use the measurement that would tell me how much space a two-dimensional object takes up. Area. If I want to know how much space a one-dimensional object takes up, I would use the measurement that tells me how much space one-dimensional objects take up, which are distances, length, meter. So that's the idea. Volume is kind of the way to talk about 3 dimensions. Area is the way to talk about 2 dimensions. Length is the way to talk about 1 dimension when we're talking about lengths, distances.
What was the point of the
Which one? This?
Yeah.
This is telling me that there's a million tiny little cubic centimeter cubes in a cube that's approximately the thing that's being laid out here.
Okay, so from the 1 meter you transmitted that.
I knew that 100 centimeters is 1 meter. And by knowing something about how dimensionality works and that that cube works like this, I can figure out that how many of those cubes will fill in that cubic meter. And these are tiny little cubes, tiny little cubic centimeters. But cubic centimeter is a very useful unit. We'll actually use both cubic meters and cubic centimeters in this class. So the final thing I want to discuss is this idea of how much stuff there is and how much space it takes up at the same time. So the way to do that is I'm going to talk. Does anyone know what this concept is called, by chance? This is called a density. Anyone heard of the idea of a density before? What is a density? How much, it's exactly what I said. How much stuff there is in a given amount of space. Okay? But if we wanted to talk about measuring it, what we do is we take the object that we want to measure, and we measure its mass. What do we measure mass in, typically? What are the units? If you were talking about imperial English units, you would use something like pounds or stone or slugs. There's all kinds of weird words for it. But what do we use in the metric system?
Gram.
Gram or kilogram. Right? That's how you measure masses. Kilo means 1,000, so 1,000 grams kilogram. There's mass, and I'm going to say how much mass in a volume, or how much mass per volume, or how much mass divided by volume is there. That's what density is. There's another way to write this. I can write it like this. I often say mass to be capital M, and volume to be capital V. And this letter looks like a fancy P, but it's not. Anyone know what this letter is? Anyone ever ever taken a Greek class. This is the Greek letter rho. R-H-O is how we write it in English. It is used because we've rapidly run out of letters. So we often use this letter to stand for density. If you don't like that letter, you can choose your own. That's fine. But that's what you'll often see. You'll often see this letter being used for density. Densities are extremely important because one of the interesting things about density is if you know that an object is basically made out of one type of material, you don't need the entire object to learn something about it in order to get the density in particular. Right? Let's say we take the Earth, for example, and I wanted to figure out the density of the Earth. Well, one way to do it is to figure out what the mass of the Earth is. That's pretty huge. And then figure out what the volume of the Earth is. That's also pretty big. And that'll work. But there's a clever way that you can get the density of the Earth without worrying about all that. And that is by taking sort of a random sample of what the Earth is made out of and measuring the mass of it and the volume of it, and you'll get the same answer. Density is something we call an intensive property. It's something that is true throughout the entire thing. A small sample will be the same as the largest part, and that's very powerful. Just know the density of a material. You can do some sort of small little calculation of a little part, and you get an answer about the whole part. So I'm going to show you how that would work. What is the Earth mostly made out of?
Water.
That's the surface. Most of the surface of the Earth is water. What about the interior?
Rock.
Rock. It's mostly rock. We, in fact, can measure the density of a random rock. And so to a good approximation, the density of that rock, which I'll call the density of the Earth, and I could write E-A-R-T-H if I wanted to, but I could also write it like this, and you'll often see me use this symbol. If I use a circle with a plus in it, that typically means the Earth. So the density of the Earth you could measure by measuring just one rock that is a fair sample of which rocks there are on the Earth. It's about 5 grams in each cubic centimeter. And I can get that just by taking a small little rock and knowing that basically the Earth is interior as a volume, as a three-dimensional object, is mostly rock. Two-dimensional, it's mostly water on a surface. Three-dimensional, it's mostly rock. One other thing I know about the Earth is that I know its radius. When you ask, how do I know the Earth is round, one of the ways this is figured out is by actually doing some measurements to calculate the radius of the Earth. This was done 2,000 years ago. People knew that the Earth was a sphere 2,000 years ago by doing some interesting calculations and measurements of shadows and the relationship between the sun and different points on the Earth. We'll get to that in that other discussion. But I will hope that you will take it as an assumption here that the radius of the Earth is about 6,300 kilometers. And this has been very well measured. So I know the radius of the Earth. If I know the radius of the Earth, do I know the volume of the Earth? Can anyone tell me how I would get that?
Google.
You could Google it, but we could calculate it without using a calculator right now. So what formula would I use? For R cubed. Draw the Earth right there. So I measured the Earth.
On top of that, you forgot the R of the Earth. The radius of the Earth is 6,300 kilometers.
Mm-hmm.
How do you get that?
This is something that you have to go out and measure.
But Professor,
You have to go out and measure it. The way you can go out and measure it is, for example, you could walk all the way around the Earth. That'd be one way of doing it. And then that would give you the circumference, and you could figure that out. That's one way to do it. Another way to do it is, I'd like to talk about that another time, how we would measure it.
Okay.
But you can go out and measure it. You have a question?
losing. I mean, he says it's like same if you measure the rock, right? It's gonna give you the same density.
Yes.
So you can just like measure like the mass of the rock and the volume of the rock.
That's right.
It's gonna be the same as.
That's right. The density will be the same. The mass won't be the same. The volume won't be the same.
Yeah, I know,
But the
just-
ratio of them won't be the same. Okay. Yeah, you have to take it as an assumption that this radius is correct, right? I haven't showed you how I measure that radius, but I can do it. It's just I need to move to other things right now. So I'm going to take that as an assumption that that's how big the radius of the Earth is, but we will discuss how we know that that's what the size of the Earth is. And this volume doesn't care. If I didn't know what this radius was, this volume would still be correct as long as I knew the Earth was a ball. So I'm going to take this V is equal to 4r cubed. And now what am I going to do? Well, I'm going to solve this. So I'm going to figure out what the volume of the Earth is. I have a 4. The R in this case is 6,300 kilometers, but I have to cube it. Well, that's okay. But I'm going to rewrite 6,300 kilometers in a different way. I'm going to write it in scientific notation. Okay? So now what I have to do is that 3 is going to hit this, it's going to hit this, and it's going to hit that. All 3 of those things. And I'll deal with each one in turn. All right? So I've got 4 still. What is going to be 6 times 6 times 6? Well, what's 6 times 6? 36. What would 36 times 3 be approximately?
36 times 3?
Yeah. So I'm going to break this down. We have 6.3, 6.3, 6.3.
No, 108.
It's about 108, but it's like close to 100, isn't it?
No, it's close to 110.
So you're gonna run
Yeah,
it to
but
300?
let's be even more general than that. If I said, is it closer to 100 or 200, you'd say it's closer to 100,
So
right?
So you just run it to 300?
So I'm going to round it, yeah. That's exactly what I'm going to do. 6 times 6, I'm going to say, is approximately 36, right? It's actually a little bit bigger than that, but that's okay. 6 times 30, I could probably say that this 6.3 is close to 2 times 3, and 36 times 3, you said, is close to 100. So it's kind of close to about 2 or 300. But actually, it doesn't really matter whether I choose 200 or 300. For our sakes, I'll just say that it's about 200. But you could say it's about 300 as well. It doesn't really matter in the end. So when I cube 6.3, I'm going to get about 200 or 300. Either one will give you an answer that's within the range of acceptable answers. When I cube 10 to the 3, what do I get? 10 to the 3 cubed. 10 to the 9. And when I cube a kilometer, I get a cubic kilometer.
You put 10 to the 3.
Thank you. 10 to the 9.
2 times 10 to the 1.
So now I'm going to do this. What's 4 times 2?
8.
8. And I have times 10 to the 2 times 10 to the 9. Is 4 times 2 8? Yeah?
Yeah.
This is like 200. So another way of writing 200 is 2 times 10 squared. Okay, so I'm just going to ignore the 10 squared. I'll keep it down here. And I've got 4 times 2 is 8.
How can you get to 200?
Yeah.
6.3 times 6.3 times 6.3. I approximated it as 200.
But
Other
what's
people
that-
approximated
what's
it.
that 2 times 3 like? What's that all about?
2 times 3 is 6. 6.3 is very close to 6.
Okay, so what, you did 36 times 6?
Exactly. And I said 36 times 3 is very close to 100. 100 times 2 is 200. Yeah. This is doing it so that I don't have to use a calculator. You could also just type this in your calculator and get the exact answer. But I want to do it without a calculator. So I'm just going to estimate. That's the idea. And if the first time you see this, it's like, what's going on, right? Like, why do we do it this way? I promise you, if you try to sort of follow along and even try to do some of the problems like this, you'll find that these calculations get more and more easy to do. They become easier.
Wait, question.
Mm-hmm.
So, because I just did 6 times 6.3 times 6.3 times 6.3, right?
Mhm.
And I got 250 something.
250 something, so that's very close to 200.
Well, if you was to round it off, it would be closer to 300.
Sure.
So,
And so someone else
So-
argued that we should say 300. Either one of those will work in this situation.
see, that's gonna confuse me because like I need to know.
You're used to, I think, in math classes, answering the question with one answer. In this class, there's more than one answer that's correct. That's just the way it is.
I see.
It's not just one answer that's correct. It's multiple
So
answers. It's a range of
Either or
possibilities.
would work.
Either or will work.
All right.
Yep. It's because it's an estimation, right? If we want it to be precisely accurate, this number is wrong, right? It's actually like 4 point something, blah, 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 right? This number is not exactly 6,300, right? This is not exactly 4r cubed. It's actually 4/3 pi r cubed. All of these things are approximations. So we have to just go with this. I know it's uncomfortable because you're used to taking math classes where they're like, you must multiply this way, this way, this way. In this class, you'll find that you'll get a slightly different answer from the other person you're working with, and both of you will be counted correct. That's the way it will work. All right, so hopefully you can follow through with these things, but I want to finish up here. So we have 8 times 10 to the 2 times 10 to the 9. What's 10 to the 2 times 10 to the 9? 10 to the 11. So that's approximately the volume of the Earth in cubic kilometers. That's the volume of the Earth in cubic kilometers. I know the density of the Earth in grams per cubic centimeter, right? Well, one of the things I could do right now, if I wanted to, is I could, by knowing that this is the volume of the Earth, and that this is the density of the Earth, figure out what the mass of the Earth is. The way that would work is I would take this density, rewrite this equation so I have density times volume is equal to mass. This is sort of what we typically do. We always do a little bit of algebra before we move on. So if I can rearrange my known fact so that I can get the thing I want to find on one side and everything else on the other, I can calculate something very interesting. And that's what I'm going to do right now. I'm going to calculate the mass of the Earth just by knowing that this is how big the Earth is and this is how dense a rock is. I'm going to figure out how, if I put the Earth on a scale, what it would weigh. So I'm going to do this, and hopefully you can follow through, but I'm going to keep these numbers around. So I have 5 grams per cubic centimeter, and I'm going to multiply that by 8 times 10 to the 11 cubic kilometers. And now I need 2 more things. Yeah?
Question: When you multiply two exponents, you're supposed to add them.
Oh, that's right. These 2.
Okay, but you got up there.
This was not multiplying. This was
cube.
power.
Okay.
Yep, and that's a very important thing to keep in mind. Whenever you're doing this, be very clear. Am I multiplying 2 things together, or am I raising them? Because you'll get the wrong answer otherwise. And that does matter. Whether I have 200 or 300 doesn't matter, but that matters. Okay.
And one more thing: how would I say the volume of the Earth?
How would you say this number?
Cubed,
I would say 8 times 10 to the 11 cubic kilometers.
cubic kilometers.
Or you could say kilometers cubed if you want. So I'm going to do this. Now, one thing I'm going to notice is that, oh, I have different units of centimeters and kilometers. That's no good. So I need to come up with a conversion factor. You could type it into Google and come up with it, but I'll let you know, and we can revisit this, what that conversion factor is. So I know that there's 1,000,000 cubic centimeters in a cubic meter. And I happen to know that there's 1 billion cubic meters in a cubic kilometer. So 1,000,000 times 1 billion is 10 to the 6 times 10 to the 9. It's 10 to the 15. It's an enormous number. But if I say that there's 10 to the 15, which is what they are, cubic centimeters in a cubic kilometer, this is the conversion factor that I need in order to get rid of my pesky volumes here. But now, look what will happen. My cubic centimeter will go away. my cubic kilometer will go away. And I'll be left with just a mass in grams. Well, what is this? What's 5 times 8?
40,
40. 10 to the 11 times 10 to the 15 is what?
26.
10 to the 26. And I've got grams. Or I could call this 4 times 10 to the 27 grams. Could I not? Is that all right?
True, okay.
And I could even convert this into kilograms if I wanted to. How would I do that? Well, 1 kilogram is 1,000 grams. So now my grams cancel, I'll end up with a kilogram. What's 10 to the 27 divided by 10 to the 3? 10 to the 24. So I say that the mass of the Earth is about 4 times 10 to the 24 kilograms, just by using this piece of information.
I think that part I remember, the last part. Right?
Ah.
Yeah.
Isn't a kilogram 1,000 grams?
Yes.
If I put gram down here, that cancels this gram.
Okay.
Kilogram doesn't cancel. 10 to the 27 divided by 10 to the 3.
Subtract the exponents.
When you divide 10 by something, by another 10 by something, you subtract the exponents. In the same way when you multiply, you add them. So I get that the mass of the Earth, which is what I was calculating here, is 4 times 10 to the 24 kilograms. Does anyone look up the mass of the Earth? Type it into Google.
Where you got the 10 power 15?